All right, quick vote. Do I wing it, or do I have a preview of the next slide available to me? What do you think? Wing it?
Wing it.
Good afternoon. I'm Richard Elling with Data Storage Systems. And I tend to pace, but I don't like to hold microphones. So hopefully I'll stay close enough that we get good audio. And if you can't hear me in the back, shout. I'll be happy to speak up. What I'd like to talk to today about is some work we do on the front end of building systems and designing systems that then we would use Brendan's or dtrace tools or the performance analysis tools to analyze in production. But really the question I wanted to talk about is how do we know if a system is going to have a chance to do this, to meet our performance goals? Before we build it, really before we spend a lot of money on capital equipment or next data center. And so we've done a lot of work over the years in the performance and applications engineering group at Sun and other useful computer measurement groups, for example. A lot of people doing performance trying to predict where we should spend our money next and get the best bang for the buck. And ZFS presents some very interesting challenges there. So I want to share then some tools that we're using and developing and have been in use for some time to help you solve this problem before you go off and spend a whole bunch of money. Then you have an idea what's going on. So that's the idea here. Now, I'm not going to go too much into the hybrid storage pool. I know Adam's going to speak about it later today. But I want to point out, as I described the hybrid storage pool, that the notion that we can build this system out to meet requirements for synchronous writes in the case of NFS serving ESX hosts, for example, or databases, or how do I optimize RAM versus L2 ARC devices, and so forth. And it's very common for people to say, hey, you know, I added a ZIL or a separate log device to my system, and it's still not faster. And we look at IOStat and we find out that the log device is saturated. Well, add another, right, is the answer. And they say, okay, I'll add another, and you add another and the performance gets better, but you're still close to saturation, so you say add another. And they say, this starts to hurt because I want to mirror those, and now I've got 6 SSDs just handling the synchronous write log. In which case, okay, we're going to tune something else. We're going to make it work, and that's a lot of the tools that tuning the SPAL, the transaction group commit interval, for example, is an excellent way where we go back and do that post facto. But before I build the data center, I still need to make these decisions. So we kind of have a good, better, best model for a hybrid storage pool that you see. And we talk about this quite a bit. And mirrors are faster than RAID Zs, and mirrors are faster than RAID 5. And stripes are faster than anything, but then you lose data. And then, so all the various ways we can build and put together a hybrid storage pool kind of boil down to what I call kind of a good, better, best. Right? I mean, the minimal one is what we have, you know, on my laptop. Although I guess that's an SSD now. But then good, you know, we had some mirroring there, maybe some RAID Z, we had some SSDs and so on and so forth. We kind of get down to this sort of best scenario scheme here. And then I come over and say, you know, if you really want to go fast, punt the hard drives, because hard drives are not fast, right? Hard drives are not fast. They're not going to be fast. Give it up. Free your mind. So when we get into then really extreme performance, then we basically had to punt hard drives. And I'll show you some good data on this in a moment. But so when we go over the top, and then you start thinking, well, what about SSDs? And the answer is, well, okay, SSDs, let's look at some data. We'll find other things with SSDs as well. But sort of from a hybrid storage pool perspective, this is what happens. Now you notice the extreme architectures get simpler Simple is good. And the reason they get simpler is because we're trying to optimize for cost. So we have hard drives, less expensive, solid state drives, more expensive. When the performance of my workload dictates that I want to go, I need a working set size that fits or doesn't fit in the various parts of the system, then I'll make a trade-off. And the trade-off is, for example, within log, if I have synchronous write activity, use ZFS to check for that, then I want a device that's faster, lower the write latency. If that device is 10x faster, or 1/10 of the latency, then it makes a good idea to make a hybrid storage pool. Okay. It turns out for hard drives, this is almost invariably the case, so we see this a lot with hard drives. But solid state drives are cool too. And when I can't get that extra 10x advantage in latency, then it doesn't necessarily make sense for me to do that, which is why the solid state disk pools are better in that regard, and they actually can cost less. Moore's law will say they'll cost less even next year. So really then what we have here is a design trade-off, and all of our engineers, our world revolves around design trade-offs. And on the left side, it's kind of like good, better, best is based on performance, but then maybe on the other side, dollars per terabyte, good, better, best is inverted, right? And so we have this dilemma that we often face in storage space, and that is space dependability and performance. You can pick two. I'm going to trade space for performance or dependability, right? And so we get it, right? We know how to do a hybrid storage pool. But the question that came about when we introduced the Thumper at Sun was, hey, I've got 48 disk drives on this thing. I use 2 for boot. And what do I do with the other 46? The answer is, do not make a single wide, 46 wide RAID Z strip, because you will be sad. For a great many ways. So I put together some models, and at the time I was in the reliability engineering group at Sun, and we do RAID subsystem analysis. And so it's like, okay, I have data protection, and our metric for that is mean time to data loss, which is a risk to losing data metric. And obviously we know double parity is better than single parity is better than no parity. Yes. And that's kind of what this graph is intended to show. I blogged this, 6 years ago or so, something like that. And so we have then mean time to data loss, how dependable it is. Better number is better. But when I do that, I trade off space. Space is the x-axis. So as I go to that 3-way mirroring, then I have less available space, which is all good and fine and dandy. And that kept me out of trouble until we also started looking at the performance, and in specifically small random read performance. Why small random read performance? Because it's the only thing I can read from a data sheet that tells me how that thing's going to work. Okay? So I haven't bought any equipment yet. I haven't built my data center. I've got data sheets from the vendors. How am I going to assess this choice of hardware? And with that, I can look at the rotational latency, rotational speed of the disk. I can look at they'll publish an average seek number. And unless you talk about the green drives, which vary their rotational speed, we can do a pretty good job of predicting what the IOPS of that drive are going to be. Then we look at the RAID, mirroring versus RAID Z, and we have a model that comes out of that, and then I have IOPS over there. And basically what you would expect is true. If I stripe everything and have no dependability, I have really good performance and lots of space. But as I add parity, I lose space, my performance goes down as well. So I'm making that 3-way trade-off. Now it's very important in this model that you do not consider caching, and this is intentional. And the reason is caching is very difficult to model. And we'll tackle that next. So the question is, for the audience in a straw vote, how many of you have heard the comment that RAID Z has the IOPS of one disk? For small random read I/O, that can be true. Okay. I'll take blame for starting that little thought process. The important thing to remember is that's the best worst case IOPS. So I still get, even to this day, people will send me email and they say, hey, your model predicted that my pool would deliver 100 IOPS and I'm getting 600 IOPS. Your model's wrong. It's like, no, actually, that's the best worst case IOPS. Yeah? In other words, the worst case you'll see is that, and the best case, anyway, this is impossible to discuss too much, so let's just say that you may have a tailwind and you're driving downhill, and I can ride my bike really fast, right? And that's a good thing to be in, but from an architect's perspective, we also have to consider that the audience will be completely full. It'll be a hot day for San Francisco, and the air conditioner doesn't quite do a job. So that's what we do in architects. So then we started to look at, okay, what about all these things with latency? And we actually noticed something really annoying. And that is, for hard drives, the IOPS number that's often quoted, and sometimes maybe you'll use 100 or 200 for your standard IOPS for a hard drive. That number works when you have one concurrent I/O sent to the drive. When I have 10 concurrent I/Os, which is the typical default for ZFS today, what we find is that the read IOPS stays fairly the same, but the actual latency, the average latency, increases dramatically. And why is this? Well, there's a scheduler in there, and he's rescheduling the I/O. And it's not that all the I/Os slow down per se, but it is a fact that those 1 second, 5 second I/Os that Brendan was discussing really show up when I issue a lot of I/Os to a disk drive. So we've put together a prototype change in ZFS to test this, and we discussed it 2 months ago or so on the forum. And the whole concept is to take a look at this data here, which basically says, as I increase the number of threads, which is the bottom x-axis, hard drive's latency falls off the cliff, or basically increases towards infinity. Right? Whereas most solid-state drives can handle a lot of I/Os. And so the problem is that hard drives can't handle a lot of I/Os. SSDs really want to handle a lot of I/Os. So how do I make the system automatically tuned for this? And that's sort of the nature of some of the work we were doing there. So let's then talk about this best worst case thing and say, we can really treat this the same way that a airplane pilot treats his aircraft, right? I have a little prop plane, and I read in the data sheet for that prop plane, it says the ceiling for this plane is 15,000 feet, let's say, for example. And what that tells me is this engine, as it's built, as it's designed for the Earth's atmosphere, right, won't be able to climb above 15,000 feet. And sometimes we call those performance envelopes. For cars, if you got a sports cars fan, it's your 0 to 60 speed or 0 to 50 speed or what have it. But there's some sort of demarcation of this bike or this car or this plane won't go faster than this, no matter how much you push it. So, so we wanted to take a look at this performance envelope and then really show it as in respect to how we design ZFS systems. So this is how we do that thing. When we hit the arc entirely, we get lots of IOPS. On a fairly inexpensive server or home desktop machine, you can get 700,000–800,000 IOPS. On a really decent server, you can get 1.4 million IOPS through ZFS hitting the arc. Okay. My little pool disks, that's running HDDs, I said like 100 per disk kind of thing. So I'm getting 1 million out of RAM, I'm getting 100 out of the pool disk. I have a log scale on the left to kind of draw this appropriately. And then I have some sort of solid-state disk that may or may not exist for the L2 arcs, right? And then once I know this information, then I can plot my working set size on the x-axis, which says basically when do I fall out of arc, or when do I fall out of the caches. And from that, then I can get a profile of what this hybrid storage pool config looks like. And that's what's broken down by arc and so forth. So then we have these points of the stair step that we can measure. So I can actually go in and measure a workload that's 100% cache hit rate. I can measure a workload that's hitting my L2 arc. I can measure my pool. Or on the other hand is we can go back to those other models that I did so long ago and say we'll use those same models with datasheet specs from vendors and fill this out. So fortunately, in the solid-state disk market today, most vendors will give you a random read IOPS number. I can calculate it from hard disk drives and then know that RAM is a lot faster and work from there. So I basically have enough information that I can build this model, and from that I can predict my pool performance. And this surprisingly works very well. And those of you who are computer architecture guys, micro-architects, will appreciate we do the same thing with CPU caches. Right? If I'm hitting first level cache, second level cache, third level cache main memory, I have the same sort of stair-step effect. And we can actually see the performance envelope on a large job. So then we can start to do what ifs, and we can put this into, in this case I put it into a little spreadsheet. We take these calculations, we have small, medium, large system. I get 3 different performance envelope curves, right? So that allows me then to change the configurations very easily. I can say, well, maybe I'll add RAM, maybe I'll add an SSD for L2 arc, maybe I'll make it bigger or whatnot, and work from there. So this becomes a pretty good tool to use. Now, one of the interesting things I found doing a lot of consulting in the field is people assume networks are infinitely fast, and I think there's actually a famous paper on this. The red line there, the horizontal red line, is like the max you'll get for 4K IOPS across a 10 gig wire. Okay, so one of the ways to think of this in a SAN environment or an NFS environment is once I get above that red line, I'm good, because I won't be able to push that through the wire. Okay, so if I'm going to model then a data center build out for a ZFS environment, I need to know something about the networks. Yeah. Well, let's throw those into the model. Oh, one slight digression. There's a really interesting and revealing benchmark suite comes out of SNIA called the Solid State Storage Performance Test Suite. And basically the idea is that for solid state storage vendors to cut down the lies, damn lies, and data sheets, they will there's a standard test procedure, and they'll profile the disk under various thread counts, IO size, read-write ratios, and so forth. So this is what I was really kind of getting around to, and this is an example of, I'm just going to a ZVol here on fairly modern, it's an old desktop, AMD Phenom 1.8 gigahertz, something like that. And you can see for the 100% read 4K IOs, yeah, I'm getting almost over 600,000 IOs, right? So don't let the marketing guys know, because they're like, oh, we can brag, we do 600,000 IOs. Yeah, but you can't get it out the 10 gig wire. Oh, yes. But this test is there. I wrote a VD bench suite to test this for you, so it'll automatically run on a device for you and give you this profile. It's really very fascinating and tells you how well engineered some of these systems are. And in this case, actually, you can tell that the default ZVol block size is 8K, right? Because it's the #1 peak there. Okay, so now then, let's take a look at a simple example. Actually, 1 week ago today, at about this time, when we were working at the ranch, we had a baby llama born. So that's him. He's unnamed. I don't know, maybe we'll call him L2R. So it's the llama arc. But basically he's my client here. Q's a button. And basically we want to look then at the system we're building out where we have networks between the clients and the ZFS devices. And so I need to model both of those. And in this case, I get a very nice predictive curve. At some point, I'll hit network saturation. Some point above network saturation, typically we can hit RAM saturation. And so I get a nice little, the green line being sort of the result of this model. So this turns out to then be pretty interesting. And for what it's worth, this is all done in a spreadsheet. So it's portable in that regard. I can give you the algorithms, right? And you can go off and build your own spreadsheet, for example. So that's kind of interesting, simple example. This one's a lot more complicated. So in this case, my llama's view is got networks, of course. Then I've got a caching layer. And that caching layer has the same sort of level 1, level 2, level 3 mode. And when at the caching level, level 3 says go off to the ZFS storage in the backside, which incidentally is on the other end of another set of networks. And what does that look like? And so we get multiple boundaries that play into this whole thing. And so kind of the dark blue cache layer line that tails down, right? So kind of this blue on the tail end downside. That's really the performance of the cache layer. And you can see as the working set size, you blow through the cache, just as we would predict. Your working set is too big for the cache, so you're going to have a lot of cache misses. And that performance is going to go, if you had no other backing store, go down. And then we get kind of interesting occurrences. For example, you'll see that the green line, which is the performance, max achievable llama's view performance, actually dips down and then increases as the working size goes up. Right? And this can be counterintuitive, but it has to do with how well and how effective and what's the performance of that caching layer as a function of the working set size. Right? And so this has been used to optimize fairly large scale build outs, and it's been able to give us an interesting view of then how do I compare two different systems which have widely varying hardware, widely varying network configurations, widely varying numbers of disks and RAID configurations and so forth, and do that comparison in some sort of logical sense so then I can put it all together. And that's what we've done there. So what else do we need to add to a model to actually go to your boss and say, I need dollars to go buy a new data center? Space. Space on disk systems is trivial. You count the bytes. That's real easy to do. In disks by size of in disks and consider RAID and you're good. Cost, we have a special deal just for you. Limited time today, 10% off. I have no idea what your costs are. Even using list prices don't make any sense. Just for grins, we periodically run these models with, you do a Google search for, the part number you want and price, and you get like 5 hits and you pick one. That's going to change drastically at all times, but the financial guys need that. There's dependability, and I've blogged extensively on dependability models and how we can do that. You can work on that and check that work out. I have some new models coming out for that would be a little bit more comprehensive and actually easier to use for an architect. But then the model I gave you was all about reads, small random reads to be precise. What about writes? Writes are really hard from a modeling perspective. There's write-back caches, there's write-back cache policies that are tunable, right? So I've got more variables in there. And more importantly, they're not readily available. There's no real good models for readily available generic workloads. Usually the way we would solve this is we'd go in the lab, fire it up, and run it and see what it looks like. Sometimes that's not very feasible. In general, in ZFS, when you write, if it's not a synchronous write, you're writing to RAM, so you get really good performance, which is cool. Guess what? A lot of other systems do that too, right? It's very common. And there's caches all the way down, including there's write caches in the disk that have to be flushed with cache flushes periodically for. So it's very, very complicated and difficult to do that. If you have any brilliant insights, I'm very interested in hearing. The other thing is, what's my predicted working set size? I have a function based on working set size, but what is it? And the answer is, you probably don't know. I've got some ideas, and I'd like to work with some ZFS folks on ideas about how to measure this on a live system. Sort of like, we have load average, and load average is a rolling average of something or another. I think we can come up with a working set size rolling average that we agree upon as being uniformly not perfect, but nevertheless useful for these sorts of analysis.
That would be great. It's a hard problem that we haven't solved yet, but it would be great.
Yeah, it's really, really hard to do, and especially without a probe effect. Yes, very, very, very challenging. So thanks for listening to my rambles today, and I hope some of these techniques and models we can help you build better data centers full of ZFS stuff. Where is Deirdre? Someone with the...
I think we're running
overtime?
behind, so...
We're a little bit behind. One question ahead.
How are you defining working set?
How am I defining working set? For this model, and that's really the crux of the question. For this model, it turns out to be just an easy way for me to give you an x-axis. Okay. For real life, we've got a really difficult problem of solving, what things fit on a real live workload. And I definitely would like to knock some heads together and see if we can't come up with a good way to do that.
Sorry, what I mean to say is working set is measured in size. You have gigabytes and terabytes, but there's necessarily a time component to it.
Yeah, right. That's the hard thing. Right?
That's correct. So this is actually, for this model, it's the instantaneous working set. Because that's easy math.
Is that 1 nanosecond? 1 millisecond?
Instantaneous. So it's the limit as time goes to zero of this function. And it just turns out to be it's easy math. It's simple algebra at that point. When you go over time, especially as we see these systems where things flow through, especially a streaming type of, we use it once, we throw it away workload, the working set size calculation becomes very much more difficult. And in that case, we're going to have a lot of cache misses, and your performance is going to be worse than this predicts. Right? So this is the best case. Everything I ask for that hits cache can hit cache case, and that's why it's the best, worst case, something or another. It's your envelope. Right. Deirdre, on time, what's next?
It is now time for a break. There are cold drinks and beers out there. I would suggest you head out for 15 minutes. We'll come back about 4.
Thank you.